Okay, so we're going to take a look at calculating delta G at non-standard state conditions. So whenever we are at standard state conditions, we just calculate delta G as equal to delta H minus T delta S, with the knots stating that they are at standard state conditions. We just look up the values of the enthalpy and the entropy in an appendix table in order to calculate delta G, or if we know the delta G of formation values, we can just use those to calculate delta G standard state condition for a reaction directly. Okay, whenever we are not at 1 atmosphere, 1 molar for a solution, or at 298 Kelvin for the temperature, then we need to do a correction for the delta G value that we would know or we would calculate initially. Okay, and this is the correction term here that needs to get added on to the delta G not at the standard state conditions that we do know. Okay, in order to get the delta G for the reaction at non-standard state conditions. Okay, so this is the equation. Delta G, this is the free energy change when you're not at standard state conditions, so there's no naught here, okay? And we have our delta G naught at standard state conditions, so either we're given that or we can calculate that from values in an appendix table. And then we're gonna add this correction term on here. It could be a positive term or it could be a negative term that we're subtracting or adding on from this value here. Okay, and this is just plus RT ln of Q. So R is the regular gas law constant that we're already familiar with. That's 8.314 joules per mole Kelvin. Okay, temperature, this is temperature in Kelvin. Okay, put that on there. Okay, temperature in Kelvin. Natural log of reaction quotient Q. Okay, so remember, this is just like K, except if we don't know if the system or the reaction is at equilibrium, then we say it's Q, and we still calculate it the same way we would calculate K. All right, so for gases, we can do that in terms of pressures, if pressures are given, or for solutions, we can use the molar concentration. So that would be pressures of products over pressures of reactants, with each with their respective mole coefficients to the exponent, okay, or concentration of products over reactants, again with the respective mole coefficients to the exponents of those. All right, so we're going to talk a little bit about here at equilibrium what happens to this reaction equation. Okay, so at equilibrium, the free energy we know ceases to change. Remember that on the pictorial diagram, depending on if it's going to reactants or products, it's always wanting to go to that minimum potential energy where the equilibrium position lies. Okay, and so when it gets to that equilibrium position, it was flat there. Okay, and so there's no change occurring there. Okay, so at equilibrium, delta G wants to approach the change of that to 0. All right, and we also know from equilibrium that if the Q we calculate for given conditions is equal to the K constant that we know, then that system has reached equilibrium, and we are at equilibrium then. Okay, if it is not equal to K, if it's greater than or less than, then the reaction system will shift either to the products or reactant side to reach equilibrium. Okay. All right, so we're going to take our equation that we have up here, and we're going to just simplify it. If we are at equilibrium, what does it become? Okay, so delta G is 0 at equilibrium. Okay, so this term here becomes 0. And now if we are at equilibrium, we can substitute K and for Q, and so we just put it in here. So we have 0 is equal to delta G naught plus RT ln of K. And then I'm just going to subtract this RT ln of K to the other side of the equation, and I get delta G naught is equal to negative RT ln of K. All right, and this is really beneficial because I can calculate delta G naught if I'm given K, or I can calculate K if I can calculate the delta G naught from the appendix table values for the specific reaction. Okay, so you can calculate what that K number is, and then based on the K number, we also know it's greater than 1, less than 1, or equal to 1, we know where the equilibrium lies. Does it lie to the product's reactants, or they're about equal amounts? Okay? So remember that, again, the K here can be in terms of pressures. Okay, it can be terms of concentration, Kc, this is Kp pressure, Kc concentrations, or it could even be in terms of, for aqueous solutions, for Ksp. You can express that in there as well. Okay, all right, so these are our three conditions, right? Whenever we had delta G was negative, it was spontaneous. Delta G was 0, it was at equilibrium. And when delta G is positive, it's a non-spontaneous condition, okay, or process. So how does that correlate with what K means as well? All right, so if the K number you know or you calculate is greater than 1, okay, K is here, all right, K is equal to concentration of products over reactants. So if K is really large, we have a lot of products. So we have a high number on our numerator here, and K will be greater than 1. All right? If K is greater than 1, what log of 1 is 0. Okay? So if we're at 1 point something, we're at greater than 1, then this here will be a positive number. ln of K will be a positive number, and we have a negative overall number that it's multiplied by here to become negative. And the negative means it is spontaneous. Okay? So when we have a lot of products, it turns out mathematically that delta G naught is negative, and that means spontaneous. And so that makes sense that it would spontaneously go to the product side based on our K number. Okay? When K is equal to 1, right, we know that these are about equal amounts of products and reactants, and we usually say that's between 0.5 and 10 for that number, not just 1, but that range 0.5 and 10. Okay? And when we do that, okay, ln of K is 0, okay, or sorry, ln of 1 is 0, so this whole term here goes to 0, and then delta G naught is equal to 0, okay? So sometimes because we use that 0.5 to that 10 range for our K number, then we have a little bit of flexibility also in what the number might turn out to be here in terms of kilojoules for the delta G naught. It might not be exactly 0 kilojoules, okay, it could be negative 10 kilojoules to positive 10 kilojoule. That's considered to be about equilibrium conditions, okay, position. Okay? All right, and then if we have K is less than 1 number, right, on our equilibrium expression here, we have a larger amount of reactants than we do products, so we would get a number over here that would be less than 1, so the reaction lies more heavily to the reactant side. If it lies heavily to the reactant side, is it going to spontaneously go to the products? No, because it's lying to the reactant side, okay? And so we know here mathematically that when K is less than 1, that will be a negative number for the natural log properties. Okay, so a negative here times a negative there gives me a positive, and that tells me that the reaction is non-spontaneous in the forward direction. Okay, which makes sense because based on the K number, it lies to the reactant side, so it's not going to the product side. However, it is spontaneous in the reverse direction. Okay, and so remember on that pictorial diagram that on this scenario here, it was going to be spontaneous in the reverse direction. Excuse me. To get to that equilibrium position where it ceases to change anymore. Okay, the first example we're going to take a look at here is a question that says we're going to use the enthalpy of formation values in order to calculate K for the specific reaction that is at 25 degrees C. So we have N2 gas plus 3H2 gas goes to 2 ammonia gas molecules. And so then I'm going to take my appendix table and look at that up, the values of the delta G of formations. And this is 0, this one is 0 for hydrogen as well, and for ammonia is minus 16.66 kilojoules per 1 mole. Okay, but I have 2 moles of them, so I'm going to multiply that number by 2. Right? So remember, you can recall that our delta G naught of reaction is equal to the sum of the delta G of formations with respect to their mole coefficients. minus the sum of the delta G of formation of the reactants with respect to their mole coefficient. So it's sum of the products minus sum of the reactants when you take into account the mole coefficients as well. Okay, so 2 moles here multiplied by a kilojoule per mole unit there gets rid of my mole units. So I already kind of account for that up here, so I don't need to do it down here. Since these are 0, then it's just this number here is the products is equal to the delta G of not of the reaction. Okay, so we're trying to calculate K, and so I know the relationship between delta G not of reaction and K. It's this equation right here that we previously just talked about. Okay, so I'm going to just substitute in the number for my delta G not of reaction here, minus 33.32 kilojoules, and then plug in my R constant, which is 8.314 joules per mole Kelvin. However, this is in kilojoules, so I'm going to go ahead and convert my joules to kilojoules for 8.314, and that gives me 0.008314, and this is per 1 mole. Okay, and I've already counted for the moles here, so I can drop out the mole unit and get joules per Kelvin. Okay, 25 degrees C correlates to 298 Kelvin, and then ln of K. So this is the variable K here that I'm solving for, the equilibrium constant. Okay, so I multiply these numbers together and divide over there, and that gives me 13.45. Okay, and whoopsies, I have a little error here. This is not in joules, this is in kilojoules. So my kelvins cancel, and then when I divide that over, my kilojoules will also cancel. Okay, which is good because our K should be unitless, right? Okay, so I multiply these numbers together and divide that by the negative 33.32, and I get 13.45. How do I get the natural log out of that? Well, I use the inverse function of the natural log. So e to that number and e to this cancels out the natural log, and I get e to the 13.45 is equal to K, and that number is 6.925 times 10 to the 5th. And again, there's no units there. But we would say, okay, this is a really large number, so the reaction lies to the product side, and the delta G naught is negative and spontaneous, so my number makes sense. Okay, this example here, we're going to calculate delta G naught of the reaction whenever we are given the equilibrium constant K value. Okay, so we're going to calculate delta G naught of reaction at 298 K. All right, and we have I2 gas plus Cl2 gas gives us 2 ICl gas, and the Kp, since we're all at gases here, this is from pressure, is 81.9. Okay, all right, so since we are given the K, okay, we are at standard conditions, so we have delta G naught, everything matches up okay. We are going to use the K value that we have and plug it in directly to solve for delta G naught. So we're just going to use this equation right here since we know the relationship between K and delta G naught of reaction. We don't need to calculate delta G naught of reaction separately from the appendix table. All right, so all we do is pretty much plug all the numbers in. So negative 8.314 joules per mole Kelvin, the temperature is 298 K, and then ln of K, which is 81.9. Just plug that in right there and calculate it out. Okay, and so we have not accounted for moles anywhere. So these moles are actually still here. And it gives us negative 1.09 times 10 to the 4th joules, or if you wanted to convert that then to kilojoules, it's minus 10.9 kilojoule per mole for the delta G naught of the reaction. All right, so now we're going to take a look at a problem where we have to use the new equation that we were talking about, where we have delta G is equal to delta G naught of a reaction plus RT ln of Q. And we're going to use this equation whenever we're calculating the Gibbs free energy for a reaction under conditions that are not at standard state. Okay? All right, so it says consider the reaction at 298 K. Okay? 2NO gas plus O2 gas goes to 2NO2 gas. And we're given the delta G naught of reaction. We could have calculated that ourselves, or we could be given that. Okay, here it's given to us, and it's negative 71.2 kilojoules. So, at standard state conditions, this specific reaction is spontaneous, okay? And the question says we want to calculate delta G of the reaction under these conditions given over here. So if I change the pressures of these, they're not all at 1 atmosphere. So when they're at 1 atmosphere, I get this number, okay? When they're not all at 1 atmosphere, under these conditions here, what is delta G? Is it still spontaneous or not? Okay, so using these conditions here, I don't know if those are at equilibrium or not. Okay, is the reaction more or less spontaneous? Okay, so we need to use this equation because we don't know if these numbers here are the conditions when the reaction is at equilibrium. Okay, so if we don't know, then we use Q. All right, and we use this equation here, and if they turn out to be equal to each other, right, then we would be at equilibrium. Okay, so I want to identify that I need to use this reaction equation, okay, or excuse me, this this mathematical equation, and I'm given the delta G naught of the reaction here. Okay, under these conditions, calculate delta G of reaction here, and so I need to account for the correction factor here. Okay, I need to account for the Q conditions, and if this turns out to be 0, then we would be, you have the same answer there, right? Okay, we would be at equilibrium. But if we're not, then what does that turn out to be? Okay, so the first thing I want to do is I want to calculate Q, because Q is going to be, you know, the equilibrium expression and concentration of products of reactants, or the pressures of the products over the pressures of the reactants raised to their respective mole coefficient values for the exponents. Okay, and so Q is equal to the pressure of the products over the pressure of the reactants. So pressure of the product would be pressure of NO2 raised to the second power for 2 moles, divided by the pressure of the reactants, which is going to be the pressure of NO raised to the second, times the pressure of O2, and that's just to the first. Okay, so that's my expression, and then now I'm going to do is just plug the numbers in. So NO2, we have 2 atmospheres there. I'm going to square that, and then NO, I have 0.1. I'm going to square that, and then O2 is 0.1, but I don't square that one. Remember, we don't include units in the K or the Q expressions, right? So I get my number there, 4.00 times 10 to the third. And now I just plug all the numbers in. So this is my delta G naught of the reaction that was given up here. This number is in kilojoules, so I'm going to convert my R constant just to kilojoules. You could convert this to joules and leave this in 8.314 joules as well. Okay, I just did it in kilojoules. And then 298 K is the temperature, ln of my Q, and I just substitute that in there. So it's more simplified if we calculate Q first rather than trying to calculate it down in here with the whole thing. Okay? And then as you work through, you should get negative 50.7 kilojoules. Okay, so that would be the delta G, Gibbs free energy for this reaction under these conditions. And the question then said, is the reaction more or less spontaneous? Well, under these conditions, it's minus 50.7, and under standard state conditions, it's minus 71. So it's smaller than the delta G naught for standard state conditions, even though it's still spontaneous, but it is less spontaneous.